STERIS TechTalk on the parametric release for ethylene oxide sterilization processing. STERIS TechTalks are a series of webinars covering subjects relating to gas and radiation sterilization processing and the laboratory testing and validation services which support these processes. My name is James Warner, and I am the Marketing Communications Manager for STERIS Applied Sterilization Technologies. I'll be the host for today's event. Our presenter today is Niel de Jager. Niel hails originally from South Africa with an undergraduate in genetics, medical board certification in microbiology, and a postgraduate qualification in pharmaceutical science. With over 10 years' experience in both the medical device industry and sterilization industry, he leans on his product knowledge in developing and rationalizing methodology in steam, irradiation, and ethylene oxide. Niel is the Validation Technical Supervisor for the Ethylene Oxide Tech Team, based in Venlo, the Netherlands. All attendees are on mute for the presentation. However, we would like to encourage everyone to submit questions using the questions function on the GoToWebinar control panel. Questions will be answered following the presentation. Today's presentation will be recorded and uploaded to our STERIS AST YouTube channel. Please note that continuing education credits are not provided as part of this webinar. So now over to Niel to begin the presentation.
Thank you, James, and good morning to everybody, and welcome to Venlo, the Netherlands, or online. I think where we start off is really just asking what is parametric release and diving into the fundamentals of parametric release. Essentially, over here, we look at validating additional process monitoring. An equation here on the left of your screen, you will see we've set up as concentration with the addition of humidity and subtracting routine BIs is equal to parametric release. The fundamentals here we're looking at is it's the same process as BI release. You don't need to have an external PCD. You will be reducing your overkill. You would have a faster routine release. You would be analyzing data in a quantitative manner as opposed to a qualitative manner, and essentially you'd be monitoring your critical parameters. So what is parametric release? So parametric release has been around formally since the first edition of ISO 11135 in 1994, but the implementation has lagged behind. And why is this? Essentially what has happened is the monitoring capabilities for parametric release have had to have a technological catch-up in terms of the concentration monitoring and your humidity measurement monitoring. To take a look into what we have over here, parametric is fundamentally a declaration that product is sterile based on records demonstrating that the process parameters were delivered within the specified tolerances. And your key concept over here is you simply replacing the routine use of a biological indicator with direct in-chamber measurement of humidity and EO concentration. Why parametric release? And really there are a number of advantages for you, the customer. What it does is it provides you a better understanding of your process dynamics. Here you can look at your trending and maintaining process effectiveness and really realize the guidance in 12.5 of ISO 11135. You will be eliminating the risks associated with BIs, risks of false positives, of routine BI handling, and risks of damage to products and pellets from placing and removal of BIs. You are moving to a qualitative release as opposed to a quantitative release methodology. So here you are, again, analyzing data, you quantitatively assessing it in accordance to your set points and tolerances. So you're not just relying on your BI yes and no data. The last advantage here is you get a faster turnaround time. And as you all know in the market, speed to market is money saved. So instead of waiting for a 2 or 7 day BI release, this is not the limiting factor in this case. So where can you find the requirements? So ISO 11135 clause 9.5.5 and clause 10.5 states that in parametric release, you need at least 2 separate monitoring locations for temperature. You need chamber humidity by direct measurement during your conditioning phase, and you need concentration determined from direct analysis of the chamber atmosphere using an analytical method. So where can I find additional technical guidance outside of the ISO 11135? Recently, the technical standard ISO 21387 was released, and in clause 9.4.2.1, it states that really how to do your parametric release validation. You can lower your control parameters during your validation for concentration, temperature, and humidity. Obviously, likewise, if you're going over to parametric release, there might be a need to repeat a few cycles at lower control parameters to widen your parametric tolerances. In addition to clause 9.4.2.1, in clause or annex A 2.3.2, 3, and 4, for temperature, it gives guidance as to the how and the where. So under temperature, here really it specifies that your parametric release validation will be the same as for your BI release validation. So you'd set your temperatures in accordance with the same method you use for BI release. For humidity, you would look at the humidity specification at the end of conditioning. And for concentration, you would look at your concentration at end of EO injection, as this is the control parameter, and your EO concentration throughout your exposure time. So why these additional requirements? Essentially, you're getting a direct assessment of the lethality variables in a quantitative fashion to give assurance of conformity against the specifications established during your validation. Now, what are these 4 variables of lethality? If we take a look at that, your 4 variables are temperature, humidity, concentration, and exposure time. And we'll be really looking into your humidity and concentration variables. As we already saw in the previous slide, your temperature is the same methodology as for a BI release validation. The how of parametric release. For temperature, you need a minimum of 2 in-chamber temperature probes. And most facilities in this day and age already have 2 in-chamber temperature probes, one for monitoring and one for control. Your parametric sensors. For EO concentration, you would have an infrared optical gas detector or a SEC sensor. And this can vary based on the EO sterilization facility's capabilities. For humidity, you could use an infrared optical gas detector, and these SEC sensors can come as dual SEC sensors that can read both ethylene oxide concentration and humidity concentration in the chamber. Or likewise, you could use a relative humidity sensor like a wireless intrinsically safe RH data logger. And here you would actually look at using more than one as a backup if one would fail during cycle. So what is the current state of affairs at the moment? So currently most manufacturers going to a parametric release method would use a run and record method. Really, you could monitor your routine process for a specified number of runs, but what is an appropriate sample set? Some customers use 30 cycles as an appropriate sample set, and based on what guidance? So this ultimately provides a narrow processing window in relation to parametric release criteria. The development by monitoring also has a fallback that you may not account for load variability like minimum and maximum loads, seasonal variability. And this is especially applicable when routine processing needs are minimal. If you're only doing one cycle per week, to get a feasible amount of runs, it would take you almost a year to set your parametric release criteria. And in this phase of routine monitoring, you would still be releasing off a BI, bringing in the BI risks. So now we would look at developing a method to validate parametric release from the beginning. This method would take less time. It would also provide for a wider, more robust release window based on new released guidance. And it's also based on a widely accepted and conservative validation method. So what we look at over here, your common process validation approaches, you would have your BI bioburden approach and your overkill approach. We'll be concentrating on an overkill approach. And this is split into two types over here, essentially your cycle calculation or your half cycle approach. With your overkill approaches, really just the basics over here, a half cycle method. What you get from a half cycle method is normally with the qualification of an external PCD, you can go beyond a 9 spore log reduction in the half cycle. And when multiplying this by 2 for your full cycle, you get greater than an 18 spore log reduction. And this equates to a 10 to the negative 12 sterility assurance level in a best case scenario. What is the requirement? The requirement is 10 to the negative 6 sterility assurance level. So here you can see you're portraying an overkill method. In your cycle calculation approach, you can calculate directly to a 12 spore reduction. And here you can calculate your precise 10 to the negative 6 sterility assurance level. So in the overkill validation. So this overkill method is by design a very robust and conservative method for validating a process. And most of you are already using this method. This presents a worst case approach and provides for a SAL well beyond your 10 to the negative 6. So looking at a worst case example. So normally just presenting a concept over here. When you do your transfer time from your preconditioning to your chamber, you could do it by means of just monitoring the transfers throughout your validation and setting the max time that was achieved. Most organizations and manufacturers and the guidance of ISO 11135 suggest having a transfer time of above 60 minutes. And in this case, you're already presenting a worst case scenario. Now, if we apply this logic to a parametric release validation. So you're already using this method to validate your sterility. So why limit to your resulting robust routine specification with a tight parametric release window? And this is where we come into the method of lowering your control parameters through your validation to qualify parametric release. So looking again at the overkill approach, your minimum requirements are in your half cycle approach, a fractional cycle, 3 half cycles and a full cycle. In your cycle calculation approach, you have a fractional cycle for PCD definition and 3 fractional cycles to assess your D value. And this is all done by the Stumbo-Murphy-Cochrane procedure. And then finally one full cycle to complete your PPQ. Now, if we take a look at parametric release through the overkill validation, your sublethal cycle can be done in a separate chamber. You'll be looking at your nominal temperature, concentration, and RH. One important fact to note is that if you're directly validating into parametric release, there's no need to qualify an external PCD. And thus you can reduce the overkill that you might be experiencing through your validation. Next, you would move to your PQ cycles for both half cycle approach and cycle calculation approach. The important factor is to include your winter simulated maximum load. From your minimum temperature, you would typically lower this by 3 degrees. Your concentration, you would target the low tolerance of your EO pressure rise. Essentially what this means is the recommended is 50 milligrams per liter lower. And for your humidity, you would target your low tolerance on your steam injection pressure rise. Moving through to your full cycle, you would validate this on a maximum load at nominal conditions, and you could carry out your residual testing on this. Additional cycle over here is if you have load variability to qualify your minimum load. And this would take the same approach as with your 3 PQ cycles at a maximum load. Just looking at an example over here, your desired routine process, you could be looking at 122 degrees Fahrenheit or 50 degrees Celsius, a greater than a 30% RH, a 300 milligram per liter concentration, and a 4-hour exposure. And that again you can see is assessed through the 4 variables of lethality. So taking a look there at the example specific, from a 50 degrees Celsius set point temperature in your PQ cycles, you would reduce this by 3 degrees to 47 degrees Celsius. You would reduce your RH by reducing the steam injection during conditioning. Your concentration, you'd reduce the delta pressure of your EO injection to get to a 250 to 270 milligrams per liter concentration. And with this, a 2-hour exposure or shorter, giving you your half cycle or your fractional cycle for cycle calculation. And this you can assess on the right-hand side against your routine cycle. So from this validation, what would be your resulting parametric release criteria? So to set your criteria for temperature, like we said before, your temperature remains the same rationale as for BI release. You've already assessed your low tolerance at 47 degrees Celsius, and that is also in conformance with the ISO. For humidity, your minimum humidity measured in chamber at the end of conditioning, and this can be determined from your PQ cycles to set a low spec on your humidity criteria. Just also considering that Annex D 6.2.2 of the ISO states that 30% is a minimum value for RH, below which failures can occur. Always remembering to take consideration for the measurement accuracy in establishing your criteria. Looking lastly at your EO concentration criteria. The concentration at the end of EO injection from PQ cycles. If you recall, the concentration injection of EO is your control measure. Then secondly, your concentration throughout gas oil, and this can be done through a number of methods. By means of your min-max concentration, by means of a time-weighted average, or with defined intervals. And then lastly, it's not uncommon to disregard the initial stabilization period of the EO dwell phase, the first 15 minutes or first 20% of exposure time. Your concentration specification will depend on the observed exposure profile of the PQ qualifications. Your profile varies based on the design of the exposure phase and your load configuration, essentially with minimum loads, variable loads, and maximum loads. Now looking into a different method If you're already on BI release and you wish to go over to parametric release, like we said before, you could do monitoring over a certain amount of cycles or time period. But if you would like to go to parametric release directly from BI release, your considerations here would be 3 performance qualification cycles at your min tolerances, as we saw before. A PQ cycle if you have a minimum load or load variability, and a full cycle just to verify your PPQ, your physical performance qualification. The assumptions that you would make over here is a successful sublethal fractional cycle in a comparative analysis is on file for the current process. You've already qualified appropriate residue release data for your current cycle. And lastly, there are no changes desired from the current routine process parameters. So in summary, with parametric release, you are replacing your routine BI by additional monitoring of in-chamber conditions. The qualifications are performed via an overkill approach, which is exactly the current approach that most customers are using currently. You're performing your physical PQ at minimum specified tolerances to establish a worst case scenario for the conditions for parametric release. Your microbiological PQ verifies the lethality of the process at these worst case PPQ conditions. In general, minimum tolerances are worst case challenges for lethality, and with this you establish your spec floor for parametric release.
Thank you again to Niel, and thanks to everyone for joining us today.